In this example, I wanted to show you how we deal with the correlated variables in dataset that we're de-identifying. So by correlated variables, I mean variables two or more where you can predict the value of one variable from another. So I'll give you some examples. If you have a date of death variable and a date of autopsy variable, then you can predict relatively accurately one date from the other. What this means is if you de-identify one variable, you really have to de-identify the other variable to the same extent. For example, if you generalize the date of death to the year of death, and you generalize the date of autopsy to the month and year of autopsy, then you'd be able to easily predict the date of death, the month and year of death from the month and year of the date of autopsy. So that's why we need to deal with correlated variables in a sensible way. So what I will do is create a data set here, or open a data set. This is the 126,000 record data set, which is the birth registry for Ontario. And in that registry, there are two correlated variables, mainly namely the date of birth of the baby and the date of discharge of the mother. Usually, discharge occurs 2 to 4 days after birth. Therefore, if you have one, you can predict the other from it, basically. So what I will do is select a number of dates. I'll select the baby's date of birth. I'll select the discharge date, and I'll select the mother's date of birth, just as to show you the impact of correlated variables when you have correlated and uncorrelated variables. Now we'll do the risk assessment, and as expected, this will show that on these three dates the risk of re-identification is very high, because these are three very specific dates. And the first thing I will do is do an automated de-identification, where I will not correlate the date of discharge and the baby's date of birth. And I'll show you the result when we do not do the correlation, and then I will run it again with the variables correlated, so you'll see the impact when we include the correlated variables. So as you can see here, 100% of the records are high risk. The risk of identification is high. So this is all expected. So now I will set up the generalization hierarchies. They're all dates, so it's pretty straightforward here. They all have the same generalization hierarchy. And in practice, the discharge date is not really very important for analysis, so I'm just going to move this all the way down and give it the least weight, the least importance. And generally, the mother's date of birth is less important than the baby's date of birth, so I'll give it a slightly less weight than the baby's date of birth. And then I'll run the automated de-identification on this data set. And this will give us a particular result, de-identification result using on these three variables. And as you will see, without correlating the variables, the baby's date of birth and the date of discharge are different, right? One is generalized more than the other. And this is problematic when you have correlated variables, as I mentioned earlier, because you can predict one from the other. So you have one variable that has more precision, even though you generalize the other correlated variable more, that generalization is irrelevant because you can predict the more precise value from it. And this will be illustrated here. So the date of birth was generalized to month and year of birth, and the discharge date to quarter and year of discharge. So essentially, even though we've managed the risk and brought it down to an acceptable level, really the discharge date is month year as well. It's more precise because we can predict the discharge date from the date of birth, right? So basically, if I'm an intruder and I don't know the exact date of birth, but I know the discharge date, the month and year of discharge, I can predict that from the date of birth, baby's date of birth, and then use that to re-identify the record. So that is problematic. So now what I'm going to do is correlate the two variables. For baby's date of birth, I'm going to say that it's correlated with discharge date. Automatically then when we go to discharge date, it has baby date of birth selected. And we'll run it again now with the correlated variables. Let me create a different data set here. So with correlated variables, it'll ensure that the amount of generalization on the two variables is exactly the same. That is guaranteed. So the baby's date of birth and the discharge date are going to have exactly the same amount of generalization. So you essentially can't bypass the generalization by using the other correlated variable. Now, other date of death, autopsy date is another example of correlated variables. Another one would be date of admission and date when a drug is started for inpatients, because often the case, the drug start date is the same day or a day after date of admission if you're looking at prescription records. Okay, so here are the results. As you can see, the baby's date of birth is month year. The discharge date is also month year. And then the mother's birth date has been generalized more to quarter year compared to the first one where it was month year. So in terms of computing the trade-offs for the generalizations in this data set, it ensured that the two correlated variables have the same level of generalization, and in this particular case, it ended up generalizing the mother's date of birth, the third variable, more than the correlated variables. That way, it guaranteed correlated variables have the same amount of de-identification, and so that you cannot predict one from the other.